One of the things you're going to be able to do for your project is to sketch a graph on your picture and then figure out what the equation for that graph is going to be. So let's practice doing that for an ellipse, for a hyperbola, and for a parabola. The ellipse is the easiest one to do. All you have to do is figure out where the center of the ellipse is. So let's say this ellipse represents maybe part of the body of my duck or something that I was making. And first of all, I locate the center, and I figure out how far, and that center is 2, -3, and how far I go in the x direction, which is 5, and in the y direction, which is 3. Using the general equation for an ellipse, and you can get that from one of your sheets, find what that is. I'm going to have x minus 2 squared, so that tells me I'm going, that's the 2 in the center. And then I'm going 5 in the x direction, so this would be 5 squared, or 25 in the denominator, plus, then the -3 is the y coordinate of the center, so this is going to be y plus 3 squared. I go 3 in the y direction, so this is 9, and then equals 1. So there's the equation of an ellipse. The hyperbola is a little trickier. If we go to the hyperbola, you had to know the dimensions. Remember, we made a little box and we had asymptotes, and the way we determined our x and y direction was from the box. Well, we don't have a box here, so we have to create our own box. So what I'm going to do is find the center first, and I can see the center is right here. It looks like the center is -5, 1. And then I can tell from the center that my y distance is 3. I can tell that that distance is 3. But I don't know my x distance. So what I'm going to do is remember that the 2 vertices of the hyperbola, the place where it changes direction, are right on the side, the middle of the box. So I'm going to draw a side of the box. I'm going to extend it fairly far out because I'm not quite sure how far it goes in the x direction. So I'm going to extend my box, and then I'm going to look at this curve here. Remember, there's an asymptote that would run diagonally through the corner of the box, through the center, and then come out the other side, and the graph would be close to that. So if I were to kind of draw a line here, it looks like it might be the asymptote. That looks pretty close to the line. It's not perfect. I'm just kind of sketching in a line. This is what you're going to have to do on your drawings. You're going to have to kind of figure that out. Now, where the corner of the line intersects the side of the, or where this line intersects where the asymptote intersects the side of the box has to be where the corner of the box is. So, and it has to be the same amount on either side. So I'm going to just kind of go with the nearest nice number that I can find. It looks like if I go 5 in each direction, here are my corners. Now I know that 5 is correct because I actually made this example. This is supposed to be 5. When you do your drawing, however, this is not, it depends how nicely your hyperbola is drawn. I have a perfectly graphed hyperbola. Your drawing might not be perfectly drawn. For one thing, most people tend to make their hyperbolas curve too much. The hyperbola does not do that. That would be a parabola. So don't make your hyperbola curve too much. Make it curve in the middle and then go very straight out to one side and the other. And so when you do this process, you may have some trial and error before you get the box correct. But once you have the box kind of drawn correctly for the hyperbola you want, then you have to determine which direction it opens. It opens in the y direction, so my y squared term is going to go first. So I'm going to have y, and here's my y coordinate of the center, y minus 1 squared. Here's my y direction, 3 squared, so this would be 9, minus x, and then here's my x coordinate, plus 5 squared, my x direction, 25 equals 1. And as I said, you're going to have to do some tweaking on this on your project to make this graph correctly. So if you need your parabola to be wider, then the box would be skinnier. If you need your parabola to be narrower, then your box is going to be more square-like. So you're going to have a long, skinny box. If you have a wide parabola, you'll have more of a square box if the parabola is closer together. And if the, of course, if I wanted a really narrow parabola, I'd have a long, skinny box, and my parabola would be opening on the ends of it like that, because my asymptotes would be like so. So that gives you some different ideas about your parabolas. Now for the hyperbola, what I want to do is actually look at my duck picture. For the parabola, I want to look at my duck picture. So here's the back of my duck, and it's a parabola. And I moved my duck off center a little for sake of making it a better example. The one that's in your notes is slightly different than this. But I would say that the vertex of this parabola looks like it's about right here. And it looks like it maybe goes through this point right here. So what you want to do is you want to come up with, as best you can, the coordinates of the vertex and one other point. And I also know that I have two different versions of my of a parabola. I know I have a y-squared version and an x-squared version. And remember, it opens in the direction of the unsquared variable. So since it's opening in the y direction, y is not squared, x is squared. So I have a couple of different ways to write this. I can write this as x minus h squared equals 4p times y minus k. Or more simply, I can write this as y is equal to some coefficient times x minus h squared plus k. So basically, this a is not equivalent to the 4p because notice in front of the x squared term. But this is more traditionally how you would see this graphed. So either way this works. Just remember 4p is just all one number. You can plug this in either way. Now the h and the k are my center point. Now my center looks like it's about negative 0.5, I'll just say 2. Negative 0.52. This point over here looks like it's 1, 2, 3, 4, 5, 6, negative 6, negative 1. So what I'm going to do is I'm going to put my center in for h and k, my negative 6, 1 in for x and y, and then I can figure out what the coefficient is, either in this form or in this form. I can figure out what that coefficient is. So maybe I'll do the first one because I think I'll maybe show you both ways. So I can say, for example, x plus 0.5 squared is equal to 4p times y minus 2. Oh, I forgot to put the x and the y in. Now I put the x and the y in, I would have negative 6 plus 0.5 squared is equal to 4p times negative 1 minus 2. Oh, I had to make this hard. So negative 5.5 squared is equal to whatever this number is times negative 3. So negative 5.5 squared divided by negative 3 is going to equal to 4p. That's going to be the number that goes right here. And then I'll have my equation. Okay, so I can figure out what that number is. And if I did it in this version, my x would be negative 6, my h would be negative 0.5, my k would be negative 1, and my y, my k would be 2, my k would be 2, and my y would be negative 1, and I'd figure out what a equals. So this is how you find this. Once you find what that number is, and I'm going to calculate it really quickly and just show you what it would look like in its final form. So I'll pause for a second. Okay, I've shown you here the two different forms of the equation and what I plugged in. So I plugged in the coordinates of the vertex, which are negative 0.52 for h and k, and I plugged in the point negative 6, negative 1 for x and y, and I solved either in this case for 4p or in this case for a. So remember, this was the general form, x minus h squared is equal to 4p times y minus k, and this was the general form, y equals a times x minus h squared plus k. They are two different ways of writing a parabola. The only, this one's probably the one on the right is probably more useful for graphing. The one on the left, this 4p, is useful if we need to find the focus. So probably for graphing, I would recommend the one on the right. But once we solve for those coefficients, so what we're trying to solve for is this number here, or this number here, I get 4p is negative 10.083, or I get a is negative 0.0992. Notice that those are just reciprocals of each other. because in this in this case, the a is the coefficient of the squared term. In this case, the 4p is the coefficient of the unsquared term. They're on opposite sides of the equal sign, so they're just reciprocals of each other. This would just be, if I move this to the other side, I'd be dividing by 4p, which would give me what a is. So once I have that, then I have my equation. So for the left-hand one, it would be x plus 0.5 squared is equal to negative 10.083 times y minus 2. If I had the other equation, I'd have y is equal to negative 0.0992 times x plus 0.5 squared plus 2. Obviously, the second one's easier to graph. So once you have that, notice that should make sense for my duck because the negative coefficient means that it's upside down. The 0.52 means it's shifted to the right, left 0.5 and up 2. Okay, so left 0.5 up 2. So that looks pretty reasonable. If I were to graph that, let's just double check to see if it looks like the back of my duck. Okay, I brought you in for the unveiling. I've typed in the equation. And I'm ready to push enter. Enter. I guess enter over here. That looks pretty good. That looks about like where I wanted it to be. So I'm fairly happy. I can adjust that if necessary, but it looks like it's going where my duck was. So if I go back and compare that, maybe I'll drag that into the graph here. And come on, there we go. If I look at that and look at my duck, does that look reasonable? Okay. It's not as, it seems like it's not as wide as I wanted it to be. So maybe I'm going to need to do a little tweaking. I don't know if maybe that's because I've got this stretched out at a different dimension. But I can actually put this with my drawing and I can see it should go through where the negative 6, 1 was. So it goes through 1, 2, 3, 4, 5. So it goes through negative 6, 1. It looks like it's the right height. So I think it may just be the way I've got my graph stretched out. It may be more stretched out on this picture and it looks wider. Also the fact that I'm cutting off, the only portion of this that I want is really from about right here to about right here. So I think that does look reasonable for my duck, or maybe a little farther. But I think I want to cut it off at the neck, so it'd be about right here to about right there. So it looks reasonable. Oh, one other thing I just wanted to tell you is when you're working on your calculator, you can get this line grid. Remember, you can check the instructions on your graphing project packet, but if you go to your menu, view, and then you can see show the grid, number 6, the grid. So you can say no grid, dot grid, or lined grid, and so it's already on line grid. If I push no grid, it would go back to this. So menu and view is where you'll find that grid. So line grid. That way it's a little easier to see what you're doing with your graph. It kind of matches your picture. Okay, well that's it. Hopefully gets you started on making equations. I don't know why that thing is flashing like crazy, but maybe if I push escape or something it'll quit flashing. There we go. And so hopefully you'll be able to get a good start on your project with this.